Thank you, Rono. Good morning, everybody. I hope you're well today. Today I'm going to speak to you about cohomology of configuration spaces of surfaces as mapping class group presentations. That's a long title. I tried to shorten it, as I said. I couldn't, so let's go for it. Let's say that as Oishi yesterday, I'm going to try to tell you like a story. So let me first tell you all about what's in the title and what are these objects that I'm considering. So sigma G1 will be my surface of genus G. Okay, I've drawn it for G equals 2. Compact oriented surface with one boundary component, finite genus. And I'm gonna write pi1 for pi1 of my surface, which is a free group on 2G elements generated by alpha 1 up to alpha 2G. I will not make any distinction between alpha i's and beta i's. They will all be alpha i's. And I guess this will be my favorite basis. But it doesn't really matter. It's just so that we have a, like, tell me if my handwriting is too small, by the way. So the loops, not that it really matters, but there will be alpha 1, alpha 2, alpha 3, alpha 4, etc. Right, that's pi 1. By h, I will be denoting the first homology of my surface. And at this point, I want to tell you that all homology today, or cohomology, will be rational. Okay? So let me write rational cohomology, unless otherwise stated. And that's just a Z2G generated by x1 up to x2G. And these are the abelianizations of those. And by configuration spaces, I will denote by Cn sigma G1 the unordered configurations. And I will not give you a definition again for this, since we've seen too many already. Finally, the mapping class group of my surface, I will denote it by gamma G1, and that's pi 0, the connected components of its diffeomorphism group. I'm taking orientation preserving diffeomorphisms that fix the boundary pointwise of my surface. And that, you might want to think about it as diffeomorphisms up to isotopy. Now, we established that if you have a map between two spaces, that doesn't induce a map between configuration spaces, but if the map is a homeomorphism, for example, then you do get a map on configuration spaces. So here I get a map of the diffeomorphism group, sorry, an action of the diffeomorphism group on configurations, and that gives an action of the mapping class group on this rational cohomology of configuration spaces on my surface. Right, and that's what I will be focusing on today. Right, so what was known about that cohomology before? There is this theorem, let me call it Theorem A, by Buddigheimer, Cohen, from, if I'm not mistaken, is it 88 or 78? I have a feeling it's 78, but I might have miswritten this down. Okay, so we have, okay, let me write it down. So we have an isomorphism of vector spaces between ith rational homology of the nth configuration space on the surface. And then let me write the right-hand side. Thank you. Yes. So, what do we have here? We express on the left-hand side we have the rational cohomology of configuration spaces. On the right-hand side, we have a bigraded algebra. I'll tell you the bigradings in a second, which is a polynomial algebra tensor, the homology of an exterior algebra. Here we have two G generators and one other generator. Same here, two G generators, another generator there. There's a differential that I can tell you if you want, but it's not the important thing today. Today I will try to focus on the action. But yes, so we have this algebra on the right, and we take the I, n part, and that gives us homology of configuration space of surfaces. So what are the bigradings? They are ya equals 2, 2, xi is 1, 1, w 0, 1, v equals 1, 2. And if these things look a bit mysterious, then I want to remember what I was saying last time I was on the board and standing here and trying to tell you a few stuff. Where we spoke, I guess, about families of configurations. And then we had something like, we had a family where just one point sits there and does nothing. So that's a zero-dimensional family of one configuration point. So that's what W is there for. We had a family where you had one point not moving and one point moving around it, one-dimensional family of two configuration points. That's what V is for. And the xi's correspond to, this would be x1, like one point moving along the loop alpha 1 or x1. And yi is when 2 points move in parallel. And then we can take products of those. That would be y3. And the first of the bigradings corresponds to homological degree, and the second corresponds to a number of points. Is my handwriting too small? Is that fine? Okay, cool. Right. So the point is that we have this, and in principle for that we can compute Betti numbers. In particular, this algebra, this homology algebra, is easy to compute, easy to understand. Let me just give some names. I want to call by R dot the bigraded algebra on the right before taking homology, and I could write this as Q generated by this span an H, right? Like a Z, like a Q to the 2G. So I can write Q generated by H in degree 2, 2, then and one-dimensional vector space in degree 0, 1, and then this polynomial in H generated, like supported in 1, Q in degree 1,2. So this is the algebra, the bigraded algebra on the right before taking homology, and I want to define H R as the algebra after taking homology. Okay, so we'll use these names later. So I told you I want to think about the action of the mapping class group. So I want to think of this as a representation of the mapping class group. I need to tell you some stuff about representation theory. So now for this, continuing with the introduction, I'm going to speak to you about some representation theory. Whenever I write rep, it will mean representation. It's just too long a word for me to write on the board. So what's the setting? For G will be a group, V a vector space, and when G acts on V by linear isomorphism, that's going to be a G rep. And then, of course, if you have a map, you can have maps between representations, and if it preserves the action of the group G, we call it G equivariant, which I shortened to G equiv map. Then we might be faced with a situation where we have a short exact sequence of G representations. And in that case, that would be something like, look something like that. I'm going to call this an extension. Not a short exact sequence, an extension of G reps. And like, I want you to remember that if we have such a situation, that does mean that E is isomorphic to V plus U as vector spaces, but it doesn't imply as G representations. The extension might not split. And I might write this, if I have an extension, I might write it as this, where this is like my extension problem. This is just how I'll be writing this. And like figuring out what E is given the V and U is an extension problem. And it will be noted like this. In general, if V is filtered by G reps, sub reps, I guess, we can take the associated graded, and then I would, like if it's something like F0 in F1, in F2, etc., up to Fn equals V, then I would write something like V equals Fn over Fn minus 1, and then all the way down to F0. So, and here, these are the multiple extension problems that we'll be facing. Right. So this is generally. Now, let's speak about the mapping class group. So, to begin with, gamma G1 acts on pi 1 by induced maps, which is, I'll remind you, F2G, free group on 2G elements. And then we get a group homomorphism, rho, from gamma G1 to automorphisms of pi 1. So, as a first observation, if we have a representation of odd pi 1, we get a representation of gamma G1 by pulling it back, by just composing with rho. Nice. Now, furthermore, gamma G1 acts on the first integral homology, which is the abelianization of the fundamental group, which is z to the 2g. So it acts by elements of GL to GZ, but we have to take care because there is an intersection product on the surface, counting intersection of curves, and the action of the mapping class group preserves this. So we get a map actually from gamma G1 to the symplectic group SP2GZ, which are matrices preserving this intersection form. And this is surjective, and so we get a short exact sequence of groups where this is the Torelli group, and it's defined to be the kernel of this action on HZ. Now, what are some representations of SP2GZ? Right. To begin with, we have H is a representation of the symplectic group. Tensor powers of H are also representations with the usual action. Exterior powers, nope, that's just a lambda. Symmetric powers, etc. And right, we can make a definition that any SP2GZ representation that is sub-rep of a quotient of H tensor n sum n is called algebraic. Okay, so these are the ones that these are the ones that are interesting somehow because these are the ones that appear here. But we have some facts which are algebraic representations are classified completely. We can give them names and we know which they are. Okay. But also, so that's nice. And also, if we have an extension problem like this of SP2GZ reps, and we know that V and U are algebraic, then we can immediately deduce that E is just that the extension splits, that V is just a direct sum. Make it clearly a direct sum. So that means that the theory is sort of semi-simple. So these things are nice because if we have a problem like this and we know that all of these are symplectic, a representation of the symplectic group, then we are sort of happy. We can just know what V is by knowing its like different bits. And now, if we have a gamma G1 representation with trivial Torelli action that means that it's an sp2gz representation. And then we can apply these results from there, and then any extension problem we could solve. A bit bigger, yes? Yes, cool. Okay, so that means that in that case, everything would be nice. We would be able to find, and I'll explain to you right now why this would be nice. The last sentence is, if the action of IG1 of the Torelli group on a gamma G1 representation is trivial, then V is an sp2gz representation. It just means that yes, if the action of this is trivial, then we get a representation of this. Right. Now, why would this be a nice scenario? Because when I started trying to solve this problem, I already knew a result by Roberto here, where we have the rational cohomology of configuration spaces of closed surfaces, and usually doing this for closed surfaces is harder than doing it for surfaces with a boundary. And we know these as as an extension problem with many bits, all of which are sp2gz reps. In fact, algebraic sp2gz representations. And that means that if we knew somehow that the action of the symplectic group on here was a priori, if the action of the mapping class group there was a priori symplectic, then we would be able to say, okay, we know the answer here by taking the direct sum there. Well, that's not true, unfortunately. And so for example, because we have a theorem by Andrea from 2020, that the action of the Torelli group on H2, C2, sigma G1 is non-trivial. So that's, we know that even if we had such a situation, we wouldn't be able to solve our extension problems immediately. Okay, so the aim is to upgrade Theorem A, which has an algebra on the right-hand side, try to give an action of gamma G1 on this algebra, and try to make this isomorphism into, let me call it star, into an isomorphism of representations of gamma G1, okay? And because I have an algebra R whose homology I'm taking, maybe it's easier to give an action on just here, which has good generators, and giving an action of a group on an algebra is like defining a map. So it would be very nice if I could just tell you how the mapping class group acts on the generators, and then extend this on the whole algebra, and then take homology, and then we get an isomorphism. That's the situation we're going to have. This is going to be true. I just have to tell you the right action. So the aim is to upgrade star to gamma G1 equivariant. Okay. Attempt one. would be, let's draw a little graph here where in the horizontal direction I'm going to have I, and in the vertical direction n. This is the first bi-degree and the second bi-degree. I'm going to write where the generators of R star star live. Let me write 0, 1, 2, 0, 1, 2. Here we just have a Q generated by 1. Here we have, let me write it with a different color, a Q generated by W. In degree 1, 1, we have an H, which is generated by the xi's. Let me write x just so that we remember that it's generated by the xi's. Here we have a Q generated by V, and in here we have the H generated by the yi's, but we also have the second exterior power of the H generated by the x's. So, okay, on W and V, we could define the action of gamma G1 to be trivial because they're just one-dimensional. So we could say, define gamma G1 to act on by the trivial action on V and W. Then on the generators X, I can treat them as a basis of H and act on them in the standard way, right? On HX as VSP2GZ. And then finally, on, I have to tell you how we act on HY, but here, really, we have, I don't want to write a direct sum. As vector spaces, it is a direct sum, but as a representation, well, we'll see in a second that it cannot be. But if I say act on HY via SP2GZ, that would mean that the Torelli group acts trivially, acts trivially on the generators of the algebra R dot dot. That would mean, in particular, that it acts trivially on the whole algebra. So on H, trivially on the homology algebra. So we would have a trivial action of the Torelli group on the right-hand side of the isomorphism star. And we already know that that's not true. So this is false. But it can be made correct. Let me call it a correct action. And this essentially, the full definition of this will be what I'll speak to you right after I write this down and I state the theorem. Yes? Yes. I want to find this, I want to find a way to be able to express this action. We have an action geometrically, but what is it? Like if you have a representation, maybe you have names for representations, and you would like to express your representation as the named representations, right? The problem is that first, we don't have named representations here yet, but I have something here, and if I am able to define the correct thing on the right, I can tell you, oh, these are isomorphic, and so this tells me what the thing is on the left. Because this might be a better way of presenting that instead of, I don't know, knowing that there's a geometric action. But yes. 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 Yes.
So I thought you gave us like geometric representatives for all these generators. So why can't we read off what the action is by just looking at, like we know what generators of Dorelius or even or Magnet-class group is. So why can't we just like look at it and see what it does?
Yes, we can do that. And that's what Andrea has done, for example, and that's how we know that the Torelli group acts non-trivially. But then you would need, if you wouldn't want to completely determine this, you would need to tell me for all generators and for all of the possible configurations, what is the answer that you would get? I'm going to give you the answer for all possible things by doing this, and it will come from something algebraic. Yes, does that answer the question? Yes.
Is there any reason a priori to have an action of the algebra R?
To have an action of the algebra. Why? Because this is expressed in terms of this by just taking I comma n, but why would I want to have an algebra? Yeah. So no, no. It is more like a hope that you could have at that point, and it turns out to be true, essentially. Like there are a few coincidences, and like I'm saying, okay, let's simplify our problem, and turns out that if we solve the simplified problem, then it actually solves the problem. Okay? Right. So the correct action will be as before, but we view R2, 2 as an extension between hy and lambda 2 hx. And I'm going to define this to be a thing called J that will be the next thing that I will define. It takes some time to find a way to define this, but the point is that if we take, when I say as before, I guess I mean these bits here. It's an extension between h generated by the y's and lambda 2h generated by the x's, okay? In the algebra R dot comma dot. This will be, I want it to be the representation J that I will define later, and with this, the point is that with this, we get that with the correct action, hi Cn sigma g1 is isomorphic to hr I comma n without the brackets as gamma g1 representations. Okay? So this will be the theorem. So that will sort of explain how to prove. And the idea is, well, now I have to tell you what this, I owe you a definition of this J, definitely.
What is now R in terms of J?
Right. The way to describe this would be let me write this like this. So you take exterior on H in degree 1, 1 plus Q in degree 0, 1. Sorry, 1, 2. Then you take the polynomial on J in degree 2, 2 and a Q in degree 1, 0, 1. So that will be the V, that will be the W. These are the yi's and these are the xi's. But then you have to quotient out, damn, okay, I'm in the corner of the board. You have to quotient out by, yes, exactly, by this, the lambda 2 of H in A 1, 1 sort of includes in J 2, 2 in the natural way, and then you quotient by that. Does it make sense? Okay. So this is R dot comma dot as an algebra, and then you take its homology and you get what you want. Okay. Any more questions?
What is it you divide out?
Yes. So that's maybe I can write it as an ideal I, and write on the next board what that ideal is. Let me start from here now then. Right, and the ideal, like, let me define an inclusion from lambda 2h into j to be the inclusion as a sub-representation, because I will define j as an extension of h by lambda 2h, okay? And I is the ideal that identifies xi wedge xj with its inclusion in it for xi wedge xj in this h lambda 2h 1, 1. Huh? Oh, again, yes. Which is h1, 1, yes. So this is the ideal, and yes, okay. Does it make sense? Okay. Okay. So from now on, I will define you that J, but I will define it in a way that we might get many more representations of the mapping class group. And then I'll sketch the proof of the theorem I stated on that blackboard. That's what I will do for the rest of the talk. It will be very brief outline. So let's see what we have here. Now, for this bit, our aim is construct some gamma G1 representations that do not come from the symplectic group. And because of the inclusion of, because of the map from rho from gamma G1 to odd pi 1, suffices that I define representations of odd pi 1. Okay? So we'll do the following construction. Okay, suffices to construct odd pi 1 representations. Okay. Consider the exterior algebra on H, which is just this, and eventually it vanishes for high degrees. It's an algebra generated by the xi's in H. Then consider this sub-objects of it. They're not algebras anymore, rather ideals. And observe that 1 plus lambda at least 1 H, so sums of wedges that have 1 in the first place. Inside here, with the multiplication, they form a group. And that's because of, we can multiply elements, but elements also have inverses, because anything of the form 1 plus something, you can use this formula, and you can get an inverse in here. Okay, so that's a group. So this is ungraded. I want this to be an ungraded. Yes, the product is the wedge. Yes, yes. And now, right. I want to define a group homomorphism theta from. Let me separate this like this. Group homomorphism theta from pi 1, which is a free group, to 1 plus lambda at least 1 H, side lambda star, that maps each generator alpha I to 1 plus xi and extend as a group homomorphism. This sounds like, this is sort of what's called a Magnus expansion. I'm just writing the name here. So we can do this. It's a non-canonical thing to do because I picked the basis in here, but that's fine. Let's see how this evaluates on a couple of elements, just so that we know what this does. Let's say I want to evaluate it on alpha 1, alpha 2. That would be theta of alpha 1 times theta of alpha 2, 1 plus x1 times 1 plus x2. That's 1 plus x1 plus x2 plus x1 wedge x2. If I evaluate it on alpha 1 inverse, then because higher wedges of xi with itself are 0, this is just 1 minus xi. This is xi. Okay. Now, up to first approximation, if you want, this is always the abelianization of the group. And then we have some higher terms. So if I decompose my theta as theta 0 plus theta 1 plus etc., so that theta I lands from pi 1 to the ith exterior power, then we observe that theta 0 is always 1. Theta 1 is the abelianization. And then, well, theta 2, who knows? That's what in my paper I called the content before I knew that it's part of something bigger. Right. So definition / proposition. We can define an action on this exterior algebra of pi 1. And we can define this as follows. This is an algebra generated as an algebra by the xi's. So I just need to tell you for phi in aught and xi, I need to tell you how it evaluates. And it will evaluate via, you take theta of phi of alpha I, and then subtract by 1. And this extends as there are a few things to check. Well, first we extend it to the whole of the algebra, and then we check that this is indeed a representation. This is a check that we can do. It's an action. But okay, let's do a sanity check just to see what happens. If phi was our identity, then identity acted on xi. That would be theta of alpha I minus 1, and that's just xi for all xi, so we're fine. If we took if we took g equals 1, so pi 1 is just a free group generated by two elements, and phi maps alpha 1 to alpha 1, alpha 2, and alpha 2 to alpha 2 inverse, then we'd have phi acted on x1, we'd get theta of alpha 1, alpha 2 minus 1. Oh, we computed this there. That's x1 plus x2 minus x1, sorry, plus x1 wedge x2. And phi acted on x2, that would be minus x2. So what do we get? That phi acts up to first approximation via the abelianization action, but then there's some extra terms coming from theta 2. Okay, so this is the abelianization action, but then there's some extra terms coming from, which are higher order terms. So let me lift that up. So for that reason, we observe that every these sub-objects I defined up there inside the full algebra are odd pi 1 sub-representations. And then we can observe that with these, the associated graded of this, it's like an extension problem, and it starts with Q, goes lambda 1h, lambda 2h, etc., up to lambda to the 2gh. This piece is like the thing that I want up there. I define J to be lambda at least 1, quotiented by lambda at least 3. That's an extension between h and lambda 2h. And we can check that if we now take this as a representation of gamma g1, IG1 acts on J non-trivially. Okay, now I've gone through all this to define J, to show that, okay, lots of other representations of gamma G1 can also appear in here, and in a sense that's the right place to look. Maybe the more correct place to look for, if you want, what I want to say, all possible representations of gamma G1 of interest. I'm making a very big claim here, but the right place to look would be, instead of taking the exterior algebra, take the completed tensor algebra, and then take all definitions as we went, and then you would get them like a wealth of representations of gamma G1. Right. So let's go to the final part, where I will outline a proof of how the two sides are, how we go back now from here to configuration spaces. Okay? I will have to state a theorem, before I state the theorem, I will have to make, well, 2-3 more quick definitions. So, take Q times to be the non-zero rationals with multiplication, okay? This is a group. If we have an action of, if we have a representation of Q times, define the kth weight space of V to be the set of vectors where every Q in V acts by multiplication by Q to the K. Q in Q. And finally, take for every D, at least 2, I guess, take a rational sphere S, D, Q, okay? And I want, and if you make your construction well, you can make sure that this rational sphere has an action of the group Q times by homeomorphisms such that every Q in Q acts by times Q on the dth homotopy group of the sphere, okay, which is Q. Now, I will state a theorem that is essentially this comes from scanning, okay, and it's in disguise. This is something that I'm allowed to do. Let me call it. This is rational equivariant. No, yes, rational equivariant and untwisted scanning, and I can explain in a second why all these words, but it states that this is also, well, not really by me, but okay. For M compact oriented manifold, D the dimension of M, and L at least 1. We can express this thing, which is what I want in my case for surfaces, as you take some desuspended reduced homology of a mapping space here. And there was an action of Q times on this sphere, so there's an action of Q times on this space, so there's an action of Q times on this vector space. I can take the nth weight space, and we have this isomorphism that is a mapping class group of M equivariant. Okay? I called this, this comes from scanning. This can be made a covariant by theorem by, okay, there are lots of names that I can say here. For example, Buttingheimer first had the idea of like doing this, but there was something else on the right-hand side. Then we could write a section space on the right-hand side because of scanning. It was made equivariant because of a theorem by Tillman and Manthorpe in 2014. And then finally, we can take the section space that would normally be here and write a mapping space instead, because we're working rationally. And we can do a trick to write this and compute the left-hand side in terms of the right-hand side, mapping class group equivariantly. Right, and so finally, what do? We would need now, in order to come back to configuration spaces, we would need to understand this space for sigma G1. So that would be map like this. We need to understand this space, Q here. I can write this as 2M, just to make it a tiny bit shorter. And I'm understanding this space by studying the Serre spectral sequence of a vibration coming from mapping from here to the base mapping space. And this map comes from restriction, pushing the whole surface a bit inside, except at one point. The thing that remains is a surface again, of the same kind, but now instead of mapping the whole boundary to the base point, you only map the base point to the base point. So we want to study this mapping space. I claim that now let's study just that. That is homotopy equivalent to maps, base maps from the wedge of 2G circles to S2MQ, and that's what a wedge here can be made a product outside. And that's just the loop space of S2MQ to the 2G. We remember that rational cohomology of that is an exterior algebra on X, tensor a polynomial algebra on Y, and we conclude by Kuhne theorem that the cohomology ring of the base space in this here is, you take this tensor with itself 2G times, so we get exterior on X1 up to X2G, tensor polynomial on Y1 up to Y2G, which I hope is familiar, is what appeared in the very beginning. It's what appears here, really. And by looking at the fiber of that, we get the W and V, and by looking at the spectral sequence, we get the differential, but we don't want to look at the differential right now. We just want to look at the action. And the thing that I need to tell you now is how does gamma G1 act on, on that, but we've studied through that. And to tell you this, after some thought, you notice, you conclude that you just need to compute the action of this on there. Which is the algebra I've written here. This has to do with permuting the loops and also pinching them. Really, the maps that you need to understand is the Hopf algebra structure of H star omega S2MQ. And what is that? Well, you have concatenation of loops right? And concatenation of loops gives you a coproduct that maps from here to the thing tensor itself, that maps the generators x to x tensor 1 plus 1 tensor x, y to y tensor 1 plus x tensor x plus y 1 tensor y. There is this bit in the middle, and from that, if you lost me, then please believe me that if I take the map phi, if I take g equals 1 again, and I take the map phi to map alpha 1 to alpha 1, alpha 2, and alpha 2 to alpha 2 inverse, this map acts on x1 by x1 plus x2, on y1 it maps it to y1 plus x1, x2 plus y2. This is the action on this algebra there. On x2 to minus x2, on y2 to minus y2, and this comes from like writing out these formulas down here. This bit is that bit there, and it's somewhere on some board that shouldn't be too far away. Where is it? It must be on up there. That's the same action as we got here by this theta 2, and that was contained in J. We recognize that as the thing I defined to be J, and that's the main part. That's where the action comes from, and that's how we get this isomorphism up there, so that on the right-hand side we have that J. I realize I'm out of time, so I will stop there, and I'll put my end of proof in a bracket. Thank you very much. Yes.
So in the end, like you say, like the entire action, it just comes from that action of like the two-step filtration.
Yes.
And that's like the first step in this, like in the Johnson filtration.
Yes.
So
So
you say everything just factors. So I don't need to understand if the first Johnson kernel has been.
yes.
The first Johnson kernel acts trivially on all.
So it's here the last sentence.
Johnson kernel
Yes.
acts trivially on all configurations.
So with the first Johnson kernel, you mean what I would call J2, and it's the kernel of the action from gamma G1 to pi 1 quotient, the second commutator subgroup, right? Yes, and yes, the point is that J2 acts trivially on J, and that means that J2 acts trivially on the whole of unordered configurations of sigma G1. No. In particular, J2 acts non-trivially if you take ordered configurations. That's a result by Bianchi, Miller, Wilson from this year. Yes. Yes. Where? Is it up there? Yes. Yes. So why the section space becomes the mapping space is because so you can understand a mapping space, sorry, a section space, if you have a bundle, right? You can take the universal bundle and you can take the classifying map, okay? You have a bundle that you want to understand. You want to understand its sections. You have a classifying map. And you want to understand the space of sections. That's the same thing as understanding the space of lifts of this map along that projection. But that space of sections, of lifts, is homotopy invariant if you take homotopies of F. If you take different choices of F that are homotopic, you get homotopic choices of this space of lifts. If this space is highly connected, you can homotope F to be, you can null homotope F. And yes, exactly. The point is that by rationalizing, essentially I have a bundle that has a fiber that looks like a sphere. If I take, we observe that I can put the right thing there so that it's contractible. In fact, I can find a right classifying space here to make it contractible. So everything contracts down, and also there's a canonical choice of F. So if you act by diffeomorphisms of M, this homotopy doesn't change. It doesn't contribute. That's how you get mapping class group equivariant. Yeah?
So what is the bubble before rationalizing?
It is you take your tangent bundle of your manifold, you fiber-wise smash it with a space. And that space is, yes, fiber-wise smash it with a space, and in this case, that space was another sphere, essentially. Okay, no. You take your tangent bundle, you take each fiber, which is an Rn, you compactify it, you add a point at infinity on every fiber, and then you fiber-wise smash that with a space X. That's how we get a sphere. Yeah.
Any other questions?
So, if I understand correctly, your argument seems that the homology of configuration spaces of surfaces, in fact, is a representation of out by one of the surface. It's not only a representation of the mapping class group, which is what one can see geometrically, but even of out by one of the surface. I mean, out of free group, including those automorphisms that don't preserve the boundary group. Is it correct? I mean, do you understand correctly?
So there is no evidence on the blackboard that would point otherwise. The evidence is because this D has to sense V to the form omega in terms of the xi's, xj's. D has to, in order to get an action here of the automorphism groups, essentially V has to be sent to an invariant tensor of the xi, xj's, and such does not exist for automorphism group. Yes. Yes.
Maybe just a small question again. In this theorem of rational equivariant untested scanning, what's the role of this L? Because it doesn't appear on the left-hand side. Is it just something I can freely choose, and that just
Yes.
on the right side the homological dimension and the
Yes. So the idea is that you would ideally want your L to be 0, so that you wouldn't have a higher sphere, you wouldn't have a shift of degrees, but you cannot do it. But as a payback, you can take it to be any positive integer, and it doesn't really matter. So
in what is that before, where you were speaking about this abstract space X, you are smashing your compactified tangent space with this is the rational 2L sphere?
yes, yes.
But this does, for some reason, not correspond to labels in your configuration space on the left side, because usually the space X you smash with is a label space.
Yes, so the idea is that if you start from this side, usually what you would get, you have an intermediate step, which is configurations on your manifold with labels in this 2L rational sphere. And then the theorem is that there is an equivariant, no, yes, there is a stable splitting of that space into configuration spaces. Yes. So there are a few steps here, and that's one of them. Yes, exactly. You use, yes, exactly. Yes.